Okay, thank you very much. Darol, thank you very much for attending our IRID conference. I want to extend my gratitude to the attendees that follow us in the National University of Colombia and in the Pedagogical and Technological University of Colombia. Our first talk today will be only available online in YouTube. So it's my pleasure then to introduce Jose Semitiel with his talk, A Two-Phase Stefan Problem with Temperature-Dependent Thermal Conductivity. So you can join the talk of Professor Semitiel in the link to YouTube that I have shared in the chat, that I sent you by email, and that you can find also in our website. So thank you very much to all of you for joining us today.
Hello, everyone. My name is Jose Semitiel, and I'm going to talk about the two-phase Stefan problem with temperature-dependent thermal conductivity, showing the work with Julieta Volati, Maria Fernanda Natale, and Domingo Tarsi. We are from Universidad Austral, Rosario, Argentina. I will divide this presentation into two parts. Firstly, we are going to prove existence of solution to a one-dimensional two-phase Stefan problem called SP for the melting of a semi-infinite material with a power-type temperature-dependent thermal conductivity, imposing a Dirichlet-type condition at the fixed phase. For this purpose, first, we are going to prove the equivalence between the Stefan problem and two coupled ordinary differential problems called P1, P2. Then, we are going to prove the existence and uniqueness of solution to the two ordinary differential problems, P1 and P2, using the Banach fixed point theorem. And then, we are going to prove the existence of at least one solution to the problem P1, P2, and this to say that the Stefan problem has at least one similarity type solution. In the second part of this presentation, we are going to obtain approximate solution to the Stefan problem, applying a heat balance integral method introduced by Good in 2001. For that, first, we are going to prove the existence and uniqueness of analytical solution to a problem defined by applying a heat balance integral method to the Stefan problem. And finally, we are going to show some numerical simulations. The two-phase Stefan problem consists on find the temperature of the liquid ration, T1, the temperature of the solid ration, T2, and the position of the free boundary S of T, such that 1 and 2 are the heat equation for the liquid and the solid phase. In 3, we impose a Dirichlet type condition at the fixed phase, and it is equal to T0. In 4, we have the phase change temperature, and it is equal to 0. In 5, the material is initially at a negative temperature, minus TR, here. And 6 is the Stefan condition. Why we consider power type temperature-dependent thermal conductivity? Because in the last years, several studies have shown that this kind of modeling can describe phase change processes with greater precision. For example, in papers like Volati, Natales, Semitiel, and Tarsia in 2022, Seretani, Salva, and Tarsia in 2018, Ekmat, Tau, Sen, and others in 2020, and Kumar, Singh, and Rahib in 2020, in all these papers, deals with one-phase Stefan problem, considering this kind of thermal conductivities. Here we generalize it to a two-phase Stefan problem where the thermal conductivities take the form 8 and 9, where delta I is a non-negative constant, Pi is greater than 1, and Ki0 are the reference thermal conductivities. Now we are going to prove the equivalence between the Stefan problem and the coupled ordinary differential problems P1, P2. Through the following change of variables, y1 and y2 given by 10, where eta is the similarity variable, the free boundary takes the form and square root of t, where it is characterized by the parameter lambda, the positive parameter lambda, to be determinate. So we have the following theorem. Under this hypothesis, the Stefan problem has a similarity type solution given by 12 to 14. If and only if the functions y1, y2, and the parameter lambda satisfy the following coupled ordinary differential problems, divide in problem P1, defined by a second-order differential equation for the function y1, with these two boundary conditions, the problem P2, defined by a second-order differential equation for the function y2, with these two boundary conditions, and the condition that couple both problems given by 21, where Stefan 1 and Stefan 2 are dimensionless parameters. Now we are going to prove the existence and uniqueness of solution to the problem P1 for the function y1. Let us consider the set K1 defined by the continuous function in the closed interval 0 lambda, such that these functions are bounded between 0 and 1. In 0 takes the value 1, and in lambda takes the value 0. Notice that this set is a subset of the Banach space of the continuous functions with the supremum norm. So we have the following theorem. Under this hypothesis, for each positive lambda, if we assume this inequality, then the function y1 in K1 is the unique solution to the problem P1 if and only if y1 is the unique fixed point of the operator f1 defined in K1 and given by 24. Now we are going to show a sketch of the proof. This is divided into 4 parts. In the first part, we are going to prove that y1 in K1 is a solution to problem P1 if and only if y1 is a fixed point of the operator f1. If y1 in K1 is a solution to the problem P1, it is easy to see that f1 is well defined, and If we consider the second order differential equation for the function y1, we make a change of variable, we integrate it, and we use the boundary condition, we can prove that y1 is a fixed point of the operator f1. The reciprocal is in a similar manner. Second, we are going to prove that f1 is a Lipschitz operator in K1. Through various computations, we can prove this relation where epsilon1 is the Lipschitz constant that depends on the parameter lambda. Third, for proof that f1 is a contractive mapping, notice that epsilon1 is an increasing function, and in infinity takes a positive value, and for each lambda, thanks to our hypothesis, epsilon1 in lambda is less than 1. So we can conclude that f1 is a contractive mapping. So in the fourth part, thanks to f1 is a contractive mapping and k1 is a closed subset of the Banach space of the continuous function in 0 lambda with the supremum norm, through the Banach fixed point theorems, we can conclude that exists a unique fixed point, y1 in k1, of the operator f1. In a similar manner, we can prove that the problem P2 for the function y2 has a unique solution. The main difference between this and the problem P1 is that here we have a restriction for lambda, which is between 0 and L, where L is the inverse of epsilon2 in 1, where epsilon2 is the Lipschitz constant of the operator f2 defined by 28. This corollary is a direct consequence of theorems 2 and 3. Under this hypothesis, if we suppose that this inequality holds, then for each lambda between 0 and L, there exists a unique solution y1 in k1 to the problem P1, and the function y2 in k2 to the problem P2. It remains to analyze the existence of solution to the equation 21 that couple both problem P1 and P2. This equation can be rewritten as in 29, where the function b depends on lambda and the functions y1 and y2. Then we have this theorem. Under this hypothesis, if these two inequalities hold, then there exists at least one solution lambda in 0L to the equation 21 that couple both problem P1 and P2. For the proof of this theorem, notice first that for each lambda between 0 and L, the function b that depends on lambda and the function y1 and y2 is between the function b1 and b2 that only depend on the parameter lambda. If we define the function w as b minus 2 lambda with lambda in 0L, it is easy to see that w in 0 is greater than b1 in 0 and it is equal to infinity, and w and L is smaller than b2 and L minus 2L, and thanks to our hypothesis is a negative constant. So we can conclude that there exists at least one root lambda in 0L to the function w, that is to say that lambda is a solution to the equation 21 that couple both problem P1 and P2. So let me sum up this first part of my presentation. Under this hypothesis, if we assume these two inequalities, then there exists at least one similarity type solution to the Stefan problem given by the temperature of the liquid ration that depends on the function y1, and y1 in k1 is the unique solution to problem P1, the temperature of the solid ration that depends on the function y2, and y2 in k1 is the unique solution to problem P2, and the free boundary that is characterized by the parameter lambda, with lambda in 0L is one solution to equation 21 that couple both problem P1 and P2. Let's now turn to the second part of my talk. We are going to obtain approximate solutions to the Stefan problem applying a heat balance integral method. This method consists on solving an approximate problem that arises when we change the heat equation by an average of them, imposing an appropriate profile for the temperature. So for the liquid phase, the heat equation from the phase change temperature transforms to the heat condition 1, which is in color red. For the solid phase, the method assumes the existence of a heat penetration depth R greater than S, called the thermal layer, beyond which there is no heat transfer. This is equivalent to assume that for each X greater than R, the heat flux in the thermal layer is equal to 0, and the temperature in the thermal layer is minus dr, that is equal to the temperature at the infinity of the original Stefan problem. By other hand, if we integrate the heat equation from S to R, we have a new condition called the heat condition 2. If we propose quadratic profiles in a space to approximate the temperatures in each phase as in 35 and 36, the free boundary takes the same form as in the original Stefan problem and square root of t, where lambda is a positive parameter to be determined. And R of t, the thermal layer, it takes the same form too, where mu is a positive parameter to be determined. This figure shows the approximate problem to the Stefan problem applying the heat balance integral method. The heat equations are changed by heat condition 1 for the liquid phase and the heat condition 2 for the solid phase. The heat flux at the thermal layer is equal to 0, and the temperature at the thermal layer is minus dr. And all the other conditions of the original Stefan problem remain the same. So we have to find the temperature of the liquid phase, the temperature of the solid phase, the free boundary, and the thermal layer. Here we prove that there exists a unique solution to the approximate problem applying a heat balance integral method to the Stefan problem. The temperature of the liquid phase is given by 37, the temperature of the solid phase are given by 38, the free boundary by 39, and the thermal layer given by 40, where the parameters A1, mu, and lambda are unique and are obtained by these expressions. Now we show numerical simulation to the solution to the Stefan problem. First, we consider the particular case where the thermal conductivities are positive constant. On the left side, we have the exact solution to the Stefan problem, and on the right side, we have the approximate solution applying the heat balance integral method to the Stefan problem. If we fix these values, in this figure we show the exact free boundary and temperature in color blue, and the approximate free boundary and the temperature in color red. From the accuracy of the heat balance integral method for constant thermal conductivity, we approximate the solution to the Stefan problem in the general case. For assured existence of solution to the two-phase Stefan problem, from Theorem 5, we select delta I, Pi, and Stefan 1 that this inequality holds. If we fix these values, we consider two examples, case 1 and case 2. Here we plot the approximate free boundary and the thermal layer for both cases, where the time is between 0 and 5. We can see that the thermal layer in both cases simulates the infinity. In this figure, we show for both cases the approximate free boundary for t between 0 and 5, and the approximate temperature for x between 0 and 2 at the time 5 seconds. In conclusion, a one-dimensional two-phase Stefan problem for the melting of a semi-infinite material with the power type temperature-dependent thermal conductivity imposing a Dirichlet condition at the fixed phase was studied. The existence of at least one analytical similarity type solution was proved using the Banach fixed point theorem. approximate solution, applying a heat balance integral method, assuming a quadratic temperature profile in space were found. The accuracy of the heat balance integral method introduced by Good with exact solution for the particular case with constant thermal conductivity was checked, and some numerical simulations were provided. Actually, we are studying numerical approximate solution to the two-phase Stefan problem using tau method based on Shift-Chebyshev polynomial, imposing a Dirichlet, a Neumann, and a Robin type boundary condition at the fixed phase. And the result of this presentation have been published in Ames Mathematics. For any question or inquiries, please email me at this address. Thanks all for your attention.
Okay, so thank you very much to Professor Jose Semitiel for this very interesting talk. This was a pre-recorded talk that we upload to YouTube with the help of EduMedios. So for questions, you can send us the question by email, and then we are going to follow the questions to Professor Semitiel. So now we have we have time to have a break, maybe 40 minutes break. So see all of you here in Google Meet for the next talk by Professor Astrid Ferici. So thank you very much for attending the conference, and see you in 40 minutes. Muchas gracias a todos por unirse. Tuvimos una charla pregrabada por el profesor José Semitiel. Estaba solamente disponible en YouTube para las preguntas. Entonces pueden compartirnos sus interrogantes por correo electrónico y se la haremos llegar al profesor Semitiel. Nos vemos aproximadamente en 40 minutos para la charla de la profesora Astrid Ferici. So, thank you very much. Okay, so we are going to start. Thank you very much to all the attendees for joining us. It's my great pleasure to present the second speaker today, Astrid Ferici from the University of Pristina, who will talk about the directional short-time fractional Fourier transform of distribution. So thank you very much, Astrid, for accepting our invitation, and please go ahead.
Thank you for accepting my presentation and this nice introduction. I am Astrid Ferici from University of Pristina, and I'm a PhD student at Kirill and Methodius University in Skopje. I'm going to present a paper called Directional Short-Time Fractional Fourier Transform of Distributions. It's a joint work with my supervisor, Katerina Sameva from Kirill and Methodius University in Skopje, and Snezana Maksimovic, a professor of Banja Luka University in Bosnia and Herzegovina. The main objectives of this presentation is to introduce a new transform, which is called directional short-time fractional Fourier transform. We will use this short name, DSTF-RFT. We aim to provide Parseval identity and the reconstruction formula for this transform. And we aim to show the continuity of this transform and its synthesis operator on appropriate space of test function. By using the duality approach, we aim to develop a distributional framework for directional short-time fractional Fourier transform on space of Schwarz-Tempest distributions. We will show that this transform and its synthesis operator can be extended as a continuous mapping between these two space of Schwarz distributions, providing that Psi is a Schwarz test function. We will show a relation between fractional Fourier transform and directional short-time fractional Fourier transform and the desingularization formula, which is in fact the inverse of this transform on a distributional framework. And at the end of the presentation, I will present several abelian and tauberian type theorems that characterize the quasi-asymptotics of distributions at the origin via the asymptotic behavior of short-time fractional Fourier transform in the fixed direction U. First, the Kober developed the first comprehensive approach of fractional Fourier transform, but in 1939. But this transform was popularized in 1980s by Namias, who was able to solve some certain class of ordinary partial differential equations arising from his study in quantum mechanics. Later on, McBride and Kerr improved this definition, and they showed that fractional Fourier transform is an isomorphism of the Schwarz space of test function unto itself. The proof is similar with the proof for Fourier transform. And they use this theory to solve some a second order ordinary differential equation that cannot be solved by classical Fourier transform. A year later, Kerr, by using the duality approach, of course, similar with the case of Fourier transform, extended this definition to the space of Tempest distributions, and he used this theory to solve some ordinary differential equations. The fractional Fourier transform of order alpha. Alpha is a real number of a function f, of an integrable function f. We denote is denoted by this symbol, is defined in the following way. The kernel of this transform is given by equality 2, where these constants C1, C2 are given as a cotangent, cosecant, and C alpha in the following way. And delta here stands for the Dirac delta function or distribution. Almeida showed that this fractional Fourier transform, which of course depends on the parameter alpha, can be seen as rotating of a signal by an angle alpha in the time frequency plane. He also showed that relation between this fractional Fourier transform and the Wigner distribution with relation with the short time Fourier transform and with the spectrogram. And of course, as other transform, this transform has been extended, several authors have studied the n-dimensional fractional Fourier transform. And the one approach is to define as a tensor product of n copies of one-dimensional fractional Fourier transform. And another approach was given by Zayat, who defined, as he called, the coupled fractional Fourier transform or two-dimensional fractional Fourier transform, which is not the tensor product of one-dimensional of two one-dimensional fractional Fourier transform. In fact, he used the Hermite function of two complex variables as in function of this transform. Here we give the definition of n-dimensional or multidimensional fractional Fourier transform of order alpha for a function, integrable function f. We denote by this symbol is defined in the following way. The kernel is given as a tensor product of the kernel of the one-dimensional fractional Fourier transform. And if we put alpha p over 2, p over 2, and so on, p over 2, we obtain the definition of the Fourier transform, classical Fourier transform. And of course, if we have this new fractional Fourier transform, we can define short-time fractional, we can define Stokes fractional, wavelet fractional, fractional wavelet transform, and so on. Short-time fractional Fourier transform was proposed by Tao. The idea is to locate the fractional Fourier domain of a signal, and of course, the n-dimensional short-time fractional Fourier transform is defined in a very easy way by Gao and Li, just by putting by getting tensor product of n copies of the one-dimensional short-time fractional Fourier transform. However, in 2021, Zayat, by using his definition of coupled fractional Fourier transform, introduced another short-time fractional Fourier transform, as he called short-time coupled fractional Fourier transform. This definition in 2023 is extended by Pilipovich, Maximovich, and Atanosova to the space of Schwarz distribution by following the duality approach. They also use the theory to study the quasi-asymptotics of distributions via the asymptotic behavior of the fractional Fourier transform and short-time fractional Fourier transform. The short-time fractional Fourier transform of order alpha of an integrable function f with respect to a window C is denoted by this symbol and is defined in a usually way. The kernel is the kernel of the fractional Fourier transform. Zayat just defined another kernel, but just in dimension the dimension of 2. So if we change this kernel, we get the definition given by Zayat. And if we put p over 2, and so on, we get the definition of a short-time Fourier transform. Candace, it is well known that wavelets are good on detecting the point singularities of signals. However, they failed where the distribution, where the singularity is well distributed, let's say like continuous curves or hyperplanes and so on. So the idea of Candace is somehow to project hyperplane continuity to point continuity, discontinuity, hyperplane discontinuity to point discontinuity by using the Radon transform and then with one-dimensional wavelet transform. He called this the transform the Ridley transform, and somehow somehow he introduced or incorporate an additional component which we call directional component U from this stands for the unit sphere of Rn in the time frequency analysis. The similar idea was followed by Grafakos and Sansing. They first used the Radon transform followed by the one-dimensional short-time Fourier transform. And so they defined the directional short-time Fourier transform of a function f with respect to a window C in the following way. However, this transform does not provide the reconstruction formula. And they overcame these difficulties by introduction what is known as a weighted Gaborich function. Give overcame this difficulty in a different way. He defined the directional short-time Fourier transform of a function f with respect to a window C in the following way. So somehow he removed the direction from the function a in power minus I x a, and now this. This transform defined by Give provides the reconstruction formula, and this definition is extended by Saniva and Atonasova to the space of tempus distributions, and it was used to study quasi-asymptotics of distributions, and to extend this transform to the space of Schwarz distribution, they used the duality approach because the direct approach is not applicable in this case. I will mention some of the spaces that we use. The Schwarz space of test function consists of all smooth functions, such that these seminoles given by a 9 are finite. This space is closed under differentiation and multiplication by polynomials. Its fresh space topology is generated by this family of seminoles, and this dual is called the space of Schwarz tempus distributions. In our study, we will write with y in power 2 and this Cartesian product, and we always suppose that n is at least 2. If n is 1, somehow we get the definition of short-time fractional Fourier transform. And we will acute the unit sphere with normalized surface area measure. We introduce the space, this space as an all smooth function, which satisfy the flowing decay condition given by 10. Here, delta U stands for the Laplace-Beltrami operator on the unit sphere. And this it is topologized in the usual way by the family of seminoles given by 10, and we denote this dual in the usual way. And in our paper, we equipped all the dual spaces by the strong dual topology. And we fix this measure as a standard measure on our set. Similar with the case of Schwarz distributions, which can, let's say, be found in Hormander book. All local integrable function f, which of at most polynomial growth. It means that the condition given by 11 is true for some constant c and a new natural number including zero. This function will be identified with distribution via the action given by 12, and this is a standard identification of a local integrable function with distribution, which has been done similar in Schwarz space for the Schwarz distributions. And here we are at our first definition. For Schwarz function C, the directional short-time fractional Fourier transform of order alpha of an integrable function f with respect to window C, we denote with this symbol, is defined in the following way. These kernels, the kernel is the same as the kernel of the fractional Fourier transform. And if we put alpha p over 2, and so on, we get the definition introduced by Gale. Since this function is not from this space, which consists all smooth functions such that all derivatives are bounded, then definition is not. Then definition 1, or given by relation 13, does not work for distributions from this space. This space consists all distributions that can be written as a finite sum of derivatives of integrable function. And it also does not work for the space of Schwarz distributions. This definition, for example, also, or this direct approach works, for example, for short-time Fourier transform or for short-time fractional Fourier transform. But in this case, this production is not a Schwarz space, so it means that this definition does not work. The first proposition, and very useful in our paper, is a relation between directional short-time fractional Fourier transform and the Fourier transform for a test function C and integrable function f. We have the following equality. Here I'm giving a sketch of the proof. In the first equality, we just give the definition of directional short-time fractional Fourier transform. In the second one, we give the definition of Dirac delta distribution. Here we use the Fubini theorem. Here we have the definition of Radon transform. Here we in the next equality we use the inversion formula for the Fourier transform. Again, we use the Fubini theorem. The next equation is just a definition of the Fourier transform, and in the last one we use what is called the Fourier slice theory. And of course, I mentioned the Parseval identity. If a C is a Schwarz function, we suppose it's not trivial, so it's not zero, and eta is a symplectic window for it. It means that this L square inner product is not zero. Then we have the following, what is known as a Parseval identity. And this is true for every f and g from this intersection of these two spaces. And of course, we have the reconstruction formula. we impose the same conditions for psi and eta, and if f is a integrable function such that its fractional Fourier transform is also integrable function, then we have the following reconstruction formula, and this reconstruction formula holds pointwisely. Here I am giving the sketch of the proof. In the second equality, we just use the first proposition, the relation between the directional short-time fractional Fourier transform and the fractional Fourier transform. In the next one, we just interchange the order of integration by using the Fubini theorem. Here, in the next one, we can change the variable of integration, and immediately we get this fractional Fourier transform for function eta. And in the last one, we use the inversion formula for the fractional Fourier transform. This is true for almost every W from Rn. And in the last equality, we use the Parseval identity for Fourier transform. And of course, we defined the space of a square integrable function over our set y in power 2n according with our choice of the standard measure, and we define the inner product in usually way, and under the condition of proposition 2. Proposition 2 was the Parseval identity. We have the following relation given by 17. If psi is a sparse function, we suppose it's non-trivial. It is non-trivial, and f is from intersection of these two spaces. Relation 17 becomes as follows. Just we put instead of gf and instead of eta psi, and we get the following equation. Since this is true for every f from this intersection, it is true also for f from Schwarz function, and since this is a dense subset of square integrable function, then we can conclude that directional short-time fractional Fourier transform can be extended to a constant. This is a constant multiply of an isometric embedding from L square integrable to L square integrable function over y in power 2n. The reconstruction formula is important for us because it tells us how we should define the synthesis operator. In our case, the directional short-time fractional synthesis operator should be defined in the following way. And if we get phi from this sparse space of test function, this integral is absolutely convergent. And if we use the reconstruction formula, we get the following relation, which is true for almost every x from Rn. The next proposition, it's easy to prove, but I will tell why it is important for us. If psi is a sparse test function and f is integrable function, we choose a phi from this space of test function, then we have the following equality. And this okay, in the first equality we just write the definition of synthesis operator, then we use the Fubini theorem, and we immediately get this equality. But under standard identification, this equality can be written as follow. This is important for us because it tells us how we should define the directional short-time fractional Fourier transform of distributions, because this is true for integrable function, and since integrable function is a subset of Schwarz distributions, it means that this should be our way. This should be our definition, as I will mention after. But first, we need the following two theorems. So the first one is theorem 5, which says that this billionaire map is given in this way is continuous, or it means that directional short-time fractional Fourier transform is a continuous map between Schwarz space of test function to this another Schwarz space of test function, providing that Psi is from Schwarz space of test function over R. And to prove that, it is enough to prove the following relation given by 20. We divided the proof in 4 steps. In the first steps, this means partial derivatives. We can integrate inside the integral, and after some calculations, we can arrive till this relation. Here we write with fd x equal with x dfx, and we write these derivatives of psi in this way. And since these two functions are again a Schwarz function, we can suppose that m and l are 0 vectors, let's say. The same as was done for the Laplace-Beltrami operator. Here, these Pj du are certain polynomials. In the similar way with Cj, we write the these derivatives of C. We write with fd this multiplication, and since these two functions are again Schwarz function, we can suppose that k is equal with 0. Of course, we need to be careful, but this is true. And for the next step, all this multiplication can be written as this operator acting in this function. Here we integrate by part and the proof in a similar way. The same is for the next step, but I will skip this part. And the next theorem is the directional short-time fractional synthesis operator is a continuous function from this set to this, providing that psi is a Schwarz test function over R. What we use here, the idea is similar with the proposition with theorem 3.2 in this paper. Is a paper written by Professor Pilipovic and his collaborators. Here we use the Parseval identity. These Fourier transforms stand for the Fourier transform of this function with respect to the second variable. Here we use the inversion formula for the fractional Fourier transform. We use the fact that the fractional Fourier transform is an isomorphism, and we end our proof in a very easy way. these two theorems, combining with the reconstruction formula, as I mentioned before, we get, let's say, the following reconstruction formula given by by relation 21. And now we are ready to define the directional short-time fraction of Fourier transform, and this synthesis operator on appropriate space of test function. First, the directional short-time fraction of Fourier transform of distribution f with respect to a window C. This C is chosen in this way. Is defined by the following duality approach, and the idea, as I mentioned, the idea comes by the proposition I mentioned before, and this definition is valid because of the continuous theorem I showed in the previous slides. And if we choose f integrable function, we can see that its definition is the same with the definition, the first definition of directional short-time fraction of Fourier transform. It means that the relation 23 is true, but this, as I said, is not true for f Schwarz-Tempers distributions. And we defined in a very natural way the directional short-time fraction of Fourier synthesis operator by this duality, and this definition is valid because of the theorem 5. The theorem 5 says that this function is from the space of test function over y in power 2m, and by using the transposes in theorem 5 and 6, we get the directional short-time fraction of Fourier transform defined as above definition 2 and 3, and definition 2 is for directional short-time fraction of Fourier transform, and definition 3 is for its synthesis operator or continuous linear maps. This is true, by under the book, let's say from Travis, we can find the theorem, and here is a reconstruction formula for the space of distributions. I earlier mentioned for the space of Schwarz space of test function, or for the Schwarz-Tempers distribution, and the proof is just by applying the definition of the synthesis operator and directional short-time fraction of Fourier transform. Here we use the definition of the reconstruction formula for the space of Schwarz function. What we noticed is if we choose a Schwarz function f and psi under the remark 1, the first equality is the remark 1. The second one is the relation between directional short-time fraction of Fourier transform and the fractional Fourier transform. First, here we interchange the order of integration by using the Fubini theorem, because we have supposed that phi is from this space, so we can interchange the rho. And under standard identification, that integral can be written in this way. So we are motivated by this relation to the following relation between a directional short-time fraction of Fourier transform and fraction of Fourier transform. So we aim we showed that this relation is true if instead of Schwarz function we obtain the Schwarz distribution f. And we use this proposition to show what is known dissimilarization formula. Dissimilarization formula, as I mentioned, is the inverse of, in this case, the inverse of a directional short-time fractional Fourier transform in the distributional framework. So here we just use the definition of synthesis operator, and in the last equality we use the previous proposition. Okay. Now, if we fix the direction in the first definition, so if we fix the direction u, we call that transform short-time fractional Fourier transform in the direction of u, and we write with this symbol. And if we put p over 2, alpha p over 2, p over 2, and so on, we get the definition which was introduced by Atanosova, Filipovic, and Saneva. And similar with the theorem for directional short-time fractional Fourier transform, we get the following relation between a short-time fractional Fourier transform in a fixed direction with the fractional Fourier transform. And by standard identification, 27 implies the relation 28, which will be used to study quasi-asymptotics of the distribution. First, we characterize the boundedness via the short-time fractional Fourier transform in a fixed direction. We choose C a Schwarz function, not a 0. A subset B is weakly or strongly bounded if and only if there exists a constant which depends on B, such that for every test function phi, we can find a constant C depends on phi and B, such that this relation is given by 29 is true. Here we use the Banach-Steinhaus theorem. If we suppose the one part, the direct part, if B is weakly bounded, it is equicontinuous. It means that there exists some constant C prime which depends on B and the natural number, so that this relation given by 30 is true for all F and phi. And then we use that nice relation, as I mentioned before. Here we just use the definition of these semi-norms. And in the last one, we use the fact that fractional Fourier transform is an isomorphism between space of short space of time function onto itself, and the converse is also easy to be proven. In the converse part we use this isomorphism, which can be found in Treves' book. The important part of theory of distribution is quasi-asymptotic behavior of distributions. We all know that distributions have no point value, and Loya-Schwitz was the first who introduced a satisfactory definition of asymptotic behavior of distributions. This definition was extended by Zaviolo as part of his investigation in quantum field theory. And later it was improved in collaboration with Vladimirov and Rozhinov. The idea is to study the asymptotic behavior of distributions by measuring it by comparing it with Karamata's slowly varying function. Karamata varying function. Okay. First, I will introduce slowly varying function, a real positive measurable function L, defined, let's say, near zero, near infinity, is called slowly varying function at the origin or respectively at the infinity if for all positive constant, any of these two relation holds true respectively. And through our presentation with L, we will write a slowly varying function at the origin. And a distribution F has quasi-asymptotic behavior of degree beta at the origin with respect to L if there exists a distribution G such that these limits hold true for every test function phi, and we use the following short.
Sorry,
Okay.
sorry, Astrid.
Yeah.
Sorry, no, just a kind reminder that you have 10 minutes
Okay.
more to finish your talk, okay?
Yeah, I will finish, I guess. And we use the following notation, and the following notation should be interpreted in the weak topology of a Schwarz-Tempers distribution. It means in the sense of equation 31. Here I will mention some of characterization of asymptotic behavior of distributions via various integral transform. Vindas, Pilipovich, and Rakic provide several abelian and Taubman theorems that characterize the quasi-asymptotics of distribution for Lyserkin space of Lyserkin distribution via wavelet transform. Again, Kostadinova, Pilipovich, Sameva, and Vindas characterize quasi-asymptotics of distribution in terms of the Riglet transform. In 2016, Pilipovich, Sameva, Vindas, Kostadinova characterized the S-asymptotic behavior of distributions in terms of the asymptotic behavior of short-time Fourier transform. Characterization of quasi-asymptotics in terms of directional short-time Fourier transform were given by Poralieva, Sameva, and Tonosova. Here we have the characterization by in terms of the Stokvel transform, and in this year we characterize the quasi-asymptotic behavior of distribution in terms of the asymptotic behavior of their Scherlet transform. In this paper, we give several abelian and Taubman theorems that characterize quasi-asymptotics of distribution at the origin. The first one is if f is a Schwarz distribution, fc is a test function with such that psi at point 0 is 1, and if f has this quasi-asymptotic behavior, and then it's a directional short-time fractional Fourier transform in the direction of u has the asymptotic quasi-asymptotic behavior given by 34. The converse is true if this set is weakly or strongly bounded in the space of Schwarz distributions. I will skip the proof. The next proposition is also a Taubman type result. So if f has quasi-asymptotic behavior of degree beta with respect to slowly varying function L, then for its directional short-time fractional Fourier transform, we have the following quasi-asymptotic behavior, and the converse is also true.
Sorry, Astrid. Sorry to disturb you. Yeah. I think that your screen is frozen. I think we are not seeing the proposition that you want to show us.
I don't know. Let's check.
Maybe,
can you see now or no?
No, maybe you can try to stop sharing and try to share again. Sorry.
That's okay. Is it
okay? Now we can Now we can see your proposition. Oh, okay, thank you.
The first proposition is Tauberian type result. If F is a Schwarz distribution and C is a test function, such Schwarz test function, such that C at point 0 is 1, then if F has this quasi-asymptotic behavior, then it's a directional short-time fractional Fourier transform has the quasi-asymptotic behavior given by 34 for every fixed parameter B, and the converse is true if this set is weakly or strongly bounded in the space of Schwarz distributions. As I said, I will skip the proof. Here we have another Tauberian type results, which says that if F has quasi-asymptotic behavior of degree beta with respect to the slowly varying function L, then we have the following quasi-asymptotic behavior related with directional short-time fractional Fourier transform in the fixed direction U, and the converse is also true. And the following, here we have another abelian type result, which says if F has quasi-asymptotic behavior of degree beta with respect to L, then for every fixed phi and parameter B, we have this limit holds true, and the convergence is uniform. Is the convergence is uniform if B lies in a bounded subset of R. I will again skip the proof of this theorem, and the Tauberian counterpart of the below proposition says that if 39 and 40 are true, then F has a quasi-asymptotic behavior of degree beta with respect to slowly varying function L. Again, I will skip the proof, but it should be mentioned that in general, similar results do not hold for quasi-asymptotics and at infinity. And here are some of the references. Most of the presentation is based on the paper which has recently been published in Journal of Pseudo-Differential Operators and its Applications. Thank you for your time.
Okay, Astrid, thank you very much for showing us your research to your topic of research related to your PhD thesis. You can keep your slides presenting. Maybe if someone has questions. So at this moment we are open for questions. Does someone has questions for Astrid? Okay. Maybe I have a question. I have a question, Astrid. Usually there are some operators that one can define using the Fourier transform, right? Like differential operators and Fourier multipliers and so on. Do you know if for this notion of fractional Fourier transform that you are investigating, are there similar notions like Fourier multipliers for this fractional Fourier transform or pseudo differential operators for this fractional Fourier transform?
I don't know.
I think maybe my question maybe doesn't make sense then in your sense maybe.
I don't know if there are some of this definition.
Right.
Maybe we should check or something.
Right. Okay. And maybe for other interested people, maybe could you mention some open problems of interest in with respect to your topic?
Yeah, there's
Maybe several open problems that you have in mind.
I don't know. I have to talk with my supervisor actually.
Okay. That's a good idea. That's a good idea. Okay, Astrid, thank you very much for sharing us
Thank you.
your very interesting talk. You are always welcome to our activities in IRCMA Latin America and this kind of series of conference that we organize with Isaac. So thank you very much.
Thank you.
So now it seems that we have a break. We are going to resume. At 18 in Central European Time with the talk of Oscar Gonzalez. Okay, so see you in 1 hour and 10 minutes. So thank you very much. Alexandra,
Okay.
Okay, so yeah,
Can you see my presentation?
just 1 second. I will introduce you first.
Okay.
So thank you very much for joining us this afternoon for the Isaac Ickman Conference. As we move to the last stretch of our second day, of course, we invite all of you to join the discussion and share with us your thoughts or questions if you have any at the end of the talk. Right, so it's truly an honor to present our next speaker, José Oscar González Cervantes from Instituto Politécnico Nacional. He's going to present on function theory induced by a fractional Pfeffer operator in the sense of Riemann-Liouville and Caputo. Okay, so thank you very much for accepting our invitation, and this is all yours. Please.
Thank you very much to organizers for do this important work. Sorry, can you see my presentation?
I can see your presentation, yes.
Thank you very much. Well,
Perfect.
I'm going to talk about the fractional function theory in quaternions. So this work is a consequence of important papers that I did with my colleague Juan Boris Reyes. So I'm going to talk about introduction, quaternionic analysis, quaternionic fractional function theory, and I'm recently fractional holomorphic function theory, a recent theory, and its consequence for quaternionic fractional derivatives. Well, first of all, we remember that holomorphic function theory has many important facts, but Stokes Borel-Pompeu formula are very important formulas, and an interesting relationship between the harmonic theory and complex analysis is given in this identity, in which the Laplace operator is decomposed in terms of the Cauchy-Riemann operator. So the hyperholomorphic function theory has a similar formulas, Stokes and Borel-Pompeu formulas, and also the Pfeffer operator decompose the Laplace operator, four-dimensional Laplace operator in this case. So these are three important properties of the hyperholomorphic function theory. So the skew field of quaternions is formed by elements X, in which X0 to X3 are real numbers, and the quaternionic imaginary units J, K, J, and K satisfies these identities. The conjugation of quaternion X is given in this case, and the product between X and its conjugation give us the quaternionic, the square of the quaternionic norm, but it coincides with the square of the norm of a four-dimensional vector, the Euclidean norm. So when we talk about the topology of quaternions, is the same of the topology of R4, the Euclidean topology. Well, given a structural set, in this case is orthonormal set, and then is a base of the R4, and also is a base of the real linear space formed by quaternions, then any quaternion can be written in this form. So we can, given a domain in quaternions, consider a quaternionic valued function in which fk is a real valued function. This will be our notation. The Pfeffer operator is given in this form, in which we can see the partials with respect to real components of the variable x. In the Stokes and the Borel-Pompeu formulas induced by this Pfeffer operator are well known, and these are given in this form. The first one is the Stokes formula, and the second one is the Borel-Pompeu formula. In the sigma is a differential form which represents the unit normal vector with the product with the differential of area. And note that the second integral appears the differential Zipf-Fueter operator. The first D is when we apply the Zipf-Fueter operator on the left, and then second D, dr, is when we apply the Zipf-Fueter operator on the right. This is because our quaternionic product is a non-commutative operation. So this second formula is the Borel-Pompeu formula. We need to remember these two important formulas. The first one, from the first one, we obtain an important extension of the Cauchy theorem. And the second formula gives us the Cauchy formula for hyperholomorphic functions. In this case, we talk about of the kernel of the Zipf-Fueter operators. Then, as you can see, the second term is equal to 0. So we obtain the Cauchy formula for quaternionic analysis in hyperholomorphic functions. Well, these two formulas are presented in these works of Shapiro and Vasilevsky. Quaternionic C-monogenic function / regular operators and boundary valued problems, the first and the second part. Well, the first work that we can see is about the quaternionic, fractional function theory in hyperholomorphic function theory. Is this higher dimensional fractional Borel-Pompeu formula and a related hypercomplex fractional operator calculus. This paper talk about the fractional calculus in monogenic functions using Clifford algebras. Well, in our case, we work with two quaternions. These two quaternions give us a 4-dimensional rectangle. MJ represents the measure of the volume volume of this 4-dimensional rectangle. So, given a quaternion in this rectangle, I consider a function, quaternionic valued function. We say that this function belongs to AC1 if for each restriction of the real components on each coordinate, we obtain a continuous differentiable and absolutely continuous function on this interval. This is a real concept. So we continue. Now, given a complex number whose real part belongs to open interval from 0 to 1, and consider 2 points in the 4-dimensional rectangle, the fractional integral in the Riemann-Liouville sense of order alpha is well known. This is a formula well known applied to the restriction of the component of our function to the coordinate xj. Note that this function is a complex valued function when we apply this fractional integral. So we know that there exists also the fractional integral on the left, in which we work with Bj. But to simplify and to short this talk, I only talk about of the left fractional integral, only of the left, but there exists the right. In the second case, we work to Bj. Well, given a quaternionic value function so defined, or it's well known that this will be a fractional integral of f, in which case is a quaternionic valued, but we apply the previous computation on each real component of our function f, and we respect the elements of the structural set. So we only apply the fractional derivative, the fractional integral on the real components of the function f. So this will be a fractional integral. Now, it's well known also that the fractional derivative in the Riemann-Liouville sense is given in this form. We only apply the partial with respect to xj. And this is the well-known fractional derivative of order alpha with respect, of f. We only apply this computation on the components, on the real components. And note that the partial is with respect to xj, in which also the integral is, the variable is xj. It's important to know this because we can see that Q0 to Q3 are another elements, are another components of another vector, another quaternion. And so, according to the previous notation, we define the fractional Zipf-Wetter operator of order alpha in this it's a natural definition. We only apply the fractional partial derivatives with respect to x1 to x3 to x0 to xc. As you can see, this is a natural definition from the previous notation. So, if we remember, quaternionic product is a non-commutative operation. So if we apply this, if we use the elements of the structural sets on the right, because in this notation we are on the left, but if we use the elements of the structural sets or on the right, we talk about of the Fueter operator, of the right fractional Fueter operator. Well, with these both notations, we can note that this is an important relationship between our C-fractional Fueter operator with the usual C-Fueter operator, in which I from A to X is the sum of these fractional integrals in the real sense. This identity is important because using this identity, we can obtain the Stokes and the Borel-Pompeu formula that we saw above, but now induced by this fractional Zipf-Wetter operator. Similarly, we can obtain this relationship for the right operators. And note, these are important conditions for our functions because we need to apply the Zipf-Wetter operator to obtain the previous formula. Then this is a version of the Stokes formula, but now we see that the fractional Fueter operators appears in the right hand. And this is an important formula to relate fractional Zipf-Wetter operator with the usual Fueter operator. And to obtain this formula, this is a consequence of the Borel-Pompeu formula. But now, in this case, we can see the fractional Zipf-Wetter operator. Note that in this previous formula, if we talk about the kernel of these fractional Zipf-Wetter operators, then this identity is equal or give us the 0, is equal to 0. So, and then we obtain a Cauchy integral theorem type for the fractional function. And if we understand that the kernel of these fractional C operators, we are going to talk about the C fractional holomorphic functions. And similarly, if the second term is 0, if this function f and g belongs to the kernel of these operators respectively, so we obtain a Cauchy formula type for this that we can see, which can be called fractional C holomorphic functions, in which K is related with the fractional Cauchy kernel, and Ant is assumed with integral, is assumed of a fractional integral in the real sense. This is a consequence of the previous formula when X coincides with Q. Note that the previous formula, Q was a fixed point in our four-dimensional rectangle, and X was a variable. But in particular, when these two quaternions coincide or are equals, we obtain this formula in this point. And if I say that if we work with the kernel of these two fractional operators, we obtain a Cauchy formula type for these functions. And particularly, if X coincides with Q, or X is equal to Q, we obtain this formula. Note that the fractional and the integral, the fractional derivative and the integral operators act on quaternionic valued functions, but the result of this application gives us a complex quaternionic functions. It is due to our alpha. And also note that our definition, sorry, I'm going to see some, in this case, note that to short this talk and for simplicity, alpha is the same complex number in each fractional integral in the real sense, but we can consider four different alphas, four different numbers. I only use one alpha to 4 fractional integrals, but it's possible to use different orders. So all these computations were presented in this work, a quaternionic fractional Borel-Pompidou type formula. And as we know, the C2, the C2, the complex number times complex number, is embedded in the quaternionic structure, in the quaternions algebra. So we obtain the results, a fractional Borel-Pompidou type formula for holomorphic function of two complex variables. But this is a consequence of the C2 is embedded in quaternions. Now, the last work is a consequence. We consider in this work the fractional slice regular functions. Practically, we use the quaternionic series. It is a good behavior that extends the complex Taylor theorem in the complex analysis. This is a consequence, but the main idea of these works are about. Now, let me. There exist another extensions. For example, if we consider a monotonously increasing function, we can talk about the fractional integral in the Riemann-Liouville sense of order alpha with respect to this monotonously increasing function phi. We can obtain this is an extension because in this case, if our function phi is the identity, this gives us the usual fractional derivative in the Riemann-Liouville sense. But also there exists another extension. We can talk about the proportional fractional derivative, which is this is a convex linear combination between our function and its fractional derivative with respect to function phi. We repeat some months ago the previous computation of the previous papers to these extensions, and we obtained these works, a fractional Borel-Pompeu formula and a related fractional Psi-Fouetter operator with respect to a vector-valued function. Also, we obtain proportional fractional holomorphic functions of two complex variables with respect to another function. This last word was recently accepted. And we repeat the previous computations, but in the bicomplex numbers to obtain on a proportional fractional bicomplex weighted fractional Borel-Pompeu formula with respect to another function. And also we add the structure of the norm square Lebesgue integral functions, the L2, the well-known L2 space, to obtain the Bergman function theory associated to a pair-to-pair fractional Psi operator. Well, this is a quaternionic fractional function theory that we obtained some months ago. But now I'm going to talk about an extension of the fractional calculus in complex analysis, but with another point of view. We saw that we define a fractional operator, but we not define a fractional derivative. These points are very different. But now we are going to talk an extension in complex analysis of a fractional derivative. So to see this, we can, to obtain this, we can see this identity. This identity is a consequence of the change of variable in the integral. This is a direct consequence of a change of variable that we can see in the argument of the function f. So the left hand, I have problems to interpret it in the plane, in the complex plane, but this the term of the right hand is a very it's more easy to interpret it in the complex sense, in the complex plane, because we only restrict our function f to a segment or line from A to X. And the point A is a fixed point. So this is an idea that we have to work with some kinds of domains. Now, this is a definition. Consider alpha in the open interval from 0 to 1 and a complex number. Let omega be a W star domain. A W star domain is a W convex domain. It's a domain in which any point of omega can be the segment from W to this element of omega. Consider the segment of line between W and this point of omega, and the segment, any segment, must be in omega. This is a W star convex. And domain because our set is an open and convex. So consider a function a continuous function. Then the complex fractional integral type of order alpha in the real Riemann-Liouville sense, of f on omega is given in this way. This is a natural definition, but in this case, W is a fixed point, and our domain is a W star domain. And also, an easy example. Consider omega a 0 star domain. Then direct computation gives us the fractional integral type of the function theta with exponent beta, where beta is a positive real number. Then we obtain this fractional complex integral. It is a direct computation. So, but we are in the complex number, so we can see the behavior of this fractional integral in holomorphic functions. In holomorphic functions, we know the power of series. So if we decompose our function in a series and we do some computations, we obtain that our function, when we applied the fractional integral or our function to our function, we obtain this new series. The first condition is necessary to the convergence of this series. To the convergence of this series, sorry. But also using well-known criteria of the complex analysis, it's possible to know convergence radio to obtain this equality in a better region. So, and as a natural extension, we saw some page ago the fractional complex integral type. And we know that in the complex analysis, d and d zeta give us the complex derivative. So this definition proposes the fractional derivative type in the Riemann-Liouville sense of f. And the formula is simple. When we use W as 0 and omega as the unit disk, is a simple formula. In particular, here our holomorphic function is a Lipschitz function of the same order, alpha. Then our formula is more easy. The derivative or formula of our function, is more easy. Then we can obtain more results when we applied this fractional operator type to holomorphic functions. In this case, is again the application of the derivative, but our function is expressed in terms of a complex series. Then derivative gives us this new series. Then another important result is a reproduction formula. This result is obtained because our holomorphic functions have an important result, is the Cauchy formula. We only applied the Cauchy formula and apply also the fractional derivative to obtain this formula. But there are more important and interesting results when we apply this fractional derivative type of order alpha to holomorphic functions, but also we can see another results on other kind of functions, but as we can see, a concept of fractional derivative of order alpha, we can extend this concept to quaternionic analysis. So in this case, given Q a quaternion and consider omega a Q star domain, remember omega is a Q star convex, is any segment line from Q to any other point of omega belongs to omega. This is the meaning of the Q star convex. And domain because it's an open and convex set. Now, denote F belongs to AC1 if and only if the function restricted to any segment, we obtain an AC1 function from the interval 0 to 1 to H. But this concept can be applied to real components. And the mapping belongs to C1. The mapping is important because we are going to apply the fractional or the conjugation of the fractional operator. So this is a natural extension of the previous concept, because in our case, if we talk about holomorphic function, hyperholomorphic function, the hyperholomorphic functions belongs to the kernel of the Fouetter operator. Then derivative is the conjugation of the Fouetter operator. That's why we can see the conjugated of the C-Fouetter operator, and this operator acts like a derivative. And the second part in the right hand, we can see the fractional derivative. So we have some unimportant results of this fractional derivative, and I'm going to omit because we are review these new computations. This formula also can be applied for C-holomorphic proportional fractional derivatives with respect to another function. So we can apply it with respect to another function using a function between f and our variable. And proportional, we can propose then a convex linear combination between this derivative and our function f. So we can extend this derivative to in the first case. In the second, we can talk about the slice regular function theory. The previous derivative can be extended to this slice regular function theory. Also, monogenic function theory, in which we will use the Dirac operator, I think, the Dirac operator. And also this computation be extended to theory of holomorphic function in several complex variables. So this is old. Thank you so much.
Okay, thank you for your talk. We are now open for questions. Does anyone have any question for Oscar? Yes, there is one question here. It says, have you thought of obtaining versions of the results in a sense other than Riemann-Liouville? That is to say, with other derivatives and fractional integrals? Also, in the multidimensional case, what would be the major difficulty in extending these fractional future operators? Thank you very much for the presentation. Yeah. Is it
Thank you
clear?
very much. Sorry, I don't understand.
Do you have access to the chat? Is it written there?
Sorry.
Maybe it's
sorry.
easier this way, yes.
Sorry, I only see my presentation because I work from my cell phone.
Okay, I can try to repeat the question. It is like this. Have you thought of obtaining versions of the results in a sense other than Riemann-Liouville? That is, with other derivatives or in fractional integrals? Also, in the multidimensional case, what would be the major difficulty in extending these fractional future operators?
Yes, Dr. Juan Bori and I have another results. We use also fractal derivative. We also add the fractal derivative, and there are more concepts can be extended.
Okay. I also have a question. Can you tell us a bit more? What is the main motivation to study this particular notion of derivative?
Well, we saw that there exists a lot of application of the fractional calculus, but unfortunately, the specialists use the real sense. I think that they don't until now use the complex analysis, because a complex number are very important. But the complex number are not used to resolve some problems. But I think that the strong property of complex number can give us more important results. This is the main idea. But we talk about quaternionic analysis, so we need to extend to more dimensions. But the main idea is to complex analysis apply to these real fractional derivatives.
Okay. Are there further questions? Okay, apparently that's not the case. So thank our speaker once again.
Thank you so much.
Okay. Okay, so we will take a small break and we continue in 15 minutes, more or less. Thank you. Okay, so after this small break, we continue with our next speaker, Professor Ricardo Abreu Blaya from Universidad Autónoma de Guerrero. Today he will speak on the Dirichlet problem for second-order elliptic systems in the ball. Professor Abreu, thank you very much for accepting our invitation, and the stage is yours. Please.
Okay, and thank you very much to the organizing committee. Thank you very much to all of you for coming. Let me present my talk. Is it possible to see it?
Yes.
Okay, thank you very much.
Thank you.
Okay. I will talk about the Dirichlet problem for inframonogenic functions. These inframonogenic functions are the solutions of some second-order partial differential equations arising in the context of Clifford analysis. It is a joint work with Arsenio Moreno Garcia from Holguín, Cuba, and Daniel Alfonso Santiesteban from Guerrero, Mexico. The Dirichlet problem is a very classical problem in analysis, which has a lot of applications in several areas, in physics as well as in engineering. Let me start with this classical Dirichlet problem for harmonic functions. In the whole of my talk, B will denote the m-dimensional ball, and partial B will be its boundary. I mean, partial B will be the m-1 dimensional sphere, okay? And the Dirichlet problem for harmonic function, which is a traditional classical matter in analysis, is to find a harmonic function in the ball which satisfies a prescribed condition on the boundary given by this function G. Okay, it is well known that in this traditional and classical context, the solution of the Dirichlet problem is given by the so-called Poisson integral, and this is in fact the unique solution of the problem. As I have mentioned before, the aim of this talk is to consider the same problem, the Dirichlet problem, but for inframonogenic functions, which are some functions appearing in the non-commutative context of Clifford analysis. These functions are defined by means of the so-called Dirac operator. The Dirac operator is a first-order differential operator defined by means of the partial derivatives and the orthogonal basis of the space, of the Euclidean space Rm. And for smooth functions defined in this space, in some domains of the n-dimensional Euclidean space, and taking values in the so-called Clifford algebras, there's small functions which belong to the kernel of this operator are referred to as monogenic functions, and it is a central concept, a central notion in the so-called Clifford analysis, which is a function theory which extend to the multidimensional context the classical complex analysis. This Dirac operator has a very nice property, and it is precisely that it factorizes the Laplacian operator. Okay, the square of the Dirac operator is exactly minus the Laplacian operator. This, of course, means that monogenic functions are in particular also harmonic. And of course, we can use this reformulation or this rewriting to define harmonic functions as the functions which belongs to the kernel of the square of the Dirac operator. Sometimes mathematics is a matter of language, and in fact, this rewriting, this simple rewriting of the harmonic equations inspires to define another equation, and it is simply to act one of the Dirac operators from the left and the other one from the right. This precisely yields to the concept of inframonogenic functions, which are exactly the solutions of this a little bit esoteric equation, because it appears in the context, in the non-commutative context of Clifford algebras, and this equation of this operator sometimes is called as sandwich operator because the F is in between the Dirac operators. Okay, and that's all. These are the inframonogenic functions. The inframonogenic functions, as far as I know, were considered in a couple of papers by the researchers Helmut Malonek, Dixon Peña, and Franz Sommen. And I think that the denominations of inframonogenic functions for the solution of this equation was given by the brilliant, recently died mathematician Franz Sommen, who is considered as one of the founders of Clifford analysis. Even when the structure of the harmonic equation and the inframonogenic equation is quite similar, it's necessary to say that harmonic functions are quite different from inframonogenic functions. Of course, if the function f is real valued, in this case, of course, harmonic functions are the same that inframonogenic functions. But in case of function taking values in Clifford algebras, it is not longer true. So the inframonogenicity does not imply the harmonicity and vice versa. Inframonogenic functions is a subclass of biharmonic functions, of course. But for inframonogenic functions, there is not a mean value property, and there is no maximum principle for such functions. Let me present now a simple example to see that. If you take this ellipsoidal domain, omega, and in Rm, and you take a vector valued polynomial given by this formula, okay, it is a one vector valued polynomial. It is possible, it's easily seen to see that really this function vanishes on the boundary of this ellipsoidal domain. Okay, and on the other hand, after some direct computations, is easily seen also that this function is indeed inframonogenic function. This means that in general, the Dirichlet problem for inframonogenic functions is, of course, ill-posed, because here you have an example of non-zero inframonogenic function vanishing on the boundary of this ellipsoidal domain. Okay. It is also remarkable that when the dimension of the space is even, we can go further. We can construct an example of a ball, an example of a function which is a non-zero inframonogenic function in the ball and vanishing on the boundary of the ball. I mean, on the n-1 dimensional sphere. The inframonogenic functions also have been studied in connection with some applications because, of course, these functions are a little bit exotic, because they appear in this non-commutative context but they are in fact related to some application, particularly in elasticity theory, and in particular in the connected to the so-called Lamé system. Here I present 4 papers about inframonogenic functions, which have been published recently. 2 of them are related with applications in these topics, the elasticity theory. Of course, there are a lot of results. It is well known that quaternionic and Clifford analysis have important applications in physics. There are a lot of papers and books related to these applications in different models of physics. But in particular, inframonogenic functions have also an important role in this direction. Okay. There are other papers recently published in the topic of inframonogenic functions, and I mean that the topic is a topic of current research. Okay. Let me again repeat the aim of this talk. The aim of this talk is to consider the Dirichlet problem for the already defined inframonogenic function, and we restrict ourselves to the case of the ball, okay, of the m-dimensional ball. We will see that the result changes if the dimension of the space is odd or the dimension of the space is even. It is a new situation which is not the case for harmonic function. Okay. Let me start with some auxiliary results which are important for our main theorems. Okay. At first, let us introduce this operator, the operator psi, which is an operator acting on the Clifford algebra R0M. The operator is defined in this way. This operator has the very nice property that the subspace of k vectors is invariant under the action of this operator. In particular, for a k vector, we can see that the action of the operator psi gives again a k vector, and following this formula. Okay? Particularly in the case of m dimension, an odd dimension, when m is odd, we have the following lemma. And this lemma says that the operator psi is a bijection. It's a bijection, and also it is possible to construct, to reproduce a formula in order to calculate the inverse of this operator. It's necessary to know that in case of m being even, it is not longer true, because of course, in case of m being even, here you can obtain 0. Okay, if we take, for example, k in such a way that 2k equals m, then we have here that psi of gk is 0 without being 0 itself. Then it means that, and it is maybe the first indication that the matters changes when the dimension of the space is even or the dimension of the space is odd. Another results that give some calculations and some relationship between the Dirac operator and this operator psi are listed here. Okay. In particular, we have in the item 3 two equalities that reveal some kind of commutation between the sandwich operator and the operator psi, as well as the Laplace operator and the operator psi. as an easy consequence of these equalities, we obtain here that when M is odd, a function is inframonogenic or harmonic in some domain if and only if the imagine of f by psi is inframonogenic or harmonic. This, in my opinion, a very symmetry result. Okay. We also use some kind of integral representation for inframonogenic function. If f belongs to this class, is C2 in the ball and C1 in the closure of the ball, and if f is inframonogenic in the ball, then it follows that f in X can be represented by this integral. It is some kind of Poisson representation formula, because here you take X in the interior domain and you can calculate it, the value of fxx, you can calculate by means of the boundary values of f and the first partial derivatives of f. Okay. It is a big difference, because here we need also the partial derivatives, which is not the case in the harmonic context. Okay, it is different, but at least we can reconstruct the values of the function of inframonogenic function in a domain by means of the values of the boundary values of the function f and its partial derivatives. Also, it is a more or less interesting lemma. We say that if f is left monogenic, remember that here we are in the context of Clifford analysis. There are functions which are left monogenic or right monogenic. It is a different concept. If f is left monogenic and x multiplied by f is right monogenic, then f has to be identically 0. And the same occurs if f is right monogenic and f is left monogenic. Okay? These are the auxiliary results we need to obtain, some of the auxiliary results we need to obtain our main results. The first result here concerning inframonogenic function say that if the dimension of the space is odd, an odd number, and the function f is a set2 function in the ball, and C1 in the closure of the ball, then if f is inframonogenic in the ball and vanishes on the boundary, then f vanishes identically in the ball. Now, this mean that, of course, here it's necessary to see here that we are assuming f to be in C2 in B and C1 in B bar, okay? A little bit more than only continuous on B bar. Under this condition, we can ensure that if f is inframonogenic in the ball and vanishes on the boundary, then f vanishes identically in the boundary. It is more or less an indicator that in the case of odd-dimensional space and in the case of the ball, it will be not so easy to find counterexamples, examples of non-zero functions, non-zero inframonogenic functions vanishing on the boundary of the domain. Okay. In other words, it means that the sphere is a set of uniqueness for inframonogenic functions. It means that if you take an inframonogenic functions which vanishes on a sphere, then this function has to be 0, of course, in the odd dimensional case. The proof of this result, I will just sketch the proofs here, is use the so-called integral representation, and because f vanishes, we obtain this formula, and we are reduced it to prove that this function here, which is denoted by capital F, this function, it vanishes identically in B, and it is proved because for the sake of brevity, It is proved because this function f, capital F, satisfies that it is right monogenic and f product with x is left monogenic, which by using one of the lemma mentioned before, we can conclude that f is identically 0. Okay, it is the proof of this simple result. No? Of course, it's based essentially based in two of the lemmas I presented. Okay. Okay, let us back to the Dirichlet problem. The Dirichlet problem for inframonogenic functions. At first, we will interested in the case of polynomials. Namely, in case when the boundary data is a polynomial. Okay. And we obtain the following result. Suppose M is odd, again, it is important to remark, M is odd, and G is a polynomial. The Dirichlet problem for inframonogenic functions on the ball with this boundary data, with polynomial boundary data, has only one solution, and it is given by this formula, where capital H here is nothing more than the solution of the Dirichlet problem for harmonic function, that we know that it is unique and is computed by the Poisson integral. Okay, it is remarkable here that the appearance of the inverse of the operator psi. Okay? It is easy to see that this function, of course, the trace of the functions on the boundary is G, because on the boundary it is 0. And then just in the boundary, this function u is equal h in x, because h is the solution of the Dirichlet problem for harmonic function. Of course, it is equal g in the boundary. And the other part, the second part, is just to prove that this function is indeed inframonogenic function, which is obtained after some rather direct computations. Of course, it depends on a lot of calculations made before. Okay, but basically, it is possible to ensure that this function is in fact inframonogenic. Okay. It means that in the case of polynomial, in the odd dimensional case, anything new appears. There is not a difference from the case of harmonic functions, because we have that for inframonogenic function, we have a unique solution, and this solution is given by this formula. Okay, in the case of polynomial, in the odd dimensional case, and in the case of the ball. But what happened, and it is an important question, what happened when G is not a polynomial itself? What happened when G is a more general, belongs to a more general class of functions? Okay, in this case, looking for a greater level of generality, then we consider the so-called higher order Lipschitz functions. Higher order Lipschitz functions, this class of functions were introduced by the mathematician Hastert Whitney, and appears the definition, the complete definition appear in the book of Stein. We will present at the end this reference. Okay. For the sake of brevity, we can say that f, a real valued function f, is assumed to be in the Lipschitz class of order 1 plus alpha if there exists a collection, this collection of function where F0 is F, and so that this field of polynomials is indeed the field of Taylor polynomials of a C1 alpha function in Rm. Of course, there is a more intrinsic definition of this class of function, which does not depend on any extension, and this definition is included in the book of Stein. But just for the sake of brevity, I prefer to say that the Lipschitz functions of order 1 plus alpha are such functions which are prepared to be extended to the whole space, m-dimensional space, as a C1 alpha function. Okay. Our next result is indeed one of our main result, and this result is about the existence of the Dirichlet problem when G is not a polynomial and when G is a function belonging to the Lipschitz class. If M is odd and G is a Lipschitz function of order 1 plus alpha, then this function, defined here, psi, the operator, defined before, P, the Poisson integral, okay? This function gives a solution of the Dirichlet problem in this class. We remark here that already we have just C continuous in B bar, or not C1, but continuous in B bar. This means that in the case of ball, and a function belonging to a Lipschitz class, you have this function given in 6 is a solution of the Dirichlet problem. To prove this theorem, we strongly use 2 results, which I will present in the next slide. I prefer do not present any proof, just to present the main tools. The first one, we call lemma 1, says that the Lipschitz class behaves invariant under the action of the Poisson operator. It is the first one, which is very important. Very important. It was proved, of course. Lemma 2 gives some kind of estimates for the norma of the first order derivative of the function of the harmonic function. Okay? And it is here. Okay, these 2 results are the main tools to obtain the proof of the existence of the Dirichlet problem when G belongs to the Lipschitz class. Okay. But what about the uniqueness? What about the uniqueness? I remember that maybe I would like to go here. In some sense, it's very close to be the uniqueness of the Dirichlet problem, but here we assume F belonging to C1 in B bar, but we need a result, similar result, but when we assume to be F just in C, just continues in B bar. No? For that reason, this theorem does not prove the uniqueness of the Dirichlet problem for the case of general case of looking for functions in this space. Okay, and then the first question is about the uniqueness. But before, I would like to mention, which is, at least for us, an open question, and is to know if for G, just in C1 on the sphere, not in Lip 1 plus alpha, but in C1, the Dirichlet problem has a solution. We don't know whether or not the Dirichlet problem has a solution for every function in C1. No. Of course, C1 is a general, is a more bigger space of function than C1 alpha. No? In any case, we conjecture that the answer to this question is in negative, but we don't know really. We have not the answer to that question. Now we will be talking about the uniqueness of the Dirichlet problem. If F is inframonogenic in B with continuous extension to B bar and vanishing trace on the sphere, then F is identically 0 in B. This theorem already state that really the Dirichlet problem for the ball in the n-dimensional case has unique solution. Okay, the proof of this theorem also is based in a couple of lemma. The first one again gives a kind of estimate for the norm of the function in the points belonging to the interior, I mean to the ball. And the second one is a kind of representation of functions by means of the psi operator and the p operator. Summarizing, we can say that in the case of odd-dimensional spaces, the results about the Dirichlet problem in the ball for functions for boundary data give in the Lipschitz classes is exactly the same as the case of harmonic function, because we have proved that it has a solution and that this solution is unique. In other words, the Dirichlet problem for inframonogenic functions under these conditions is well posed. Okay. But what happened when the dimension of the space is even? Is even. Okay. I go back just to the first slides to remember the situation here. That this lemma about this good property of psi to be a bijection in the case of odd-dimensional space is no longer true for the case of even-dimensional space. And this algebraic situation, algebraic difficulties imply some difficulties also when we consider the Dirichlet problem in the case of even-dimensional spaces. We will see now what I am talking. Okay, the case of even dimension. The first is a counterexample to the uniqueness. If you suppose that M is even and take K to be the middle of M, okay, M divided by 2. In other words, M equals to K, and chose an arbitrary K vector valued function which is left monogenic. It is well known that K vector valued functions which are left monogenic are also right monogenic. Of course, are a lot of K vector valued functions which are left and right monogenic. In other terminology, these k-vector value functions are called harmonic k-vector field. Okay, harmonic k-vector field. And suppose that it is the case in a domain omega containing the ball. And take this function, this very simple function. When I say the ball, I say the unit ball, okay? In any case. And take this function, the unit ball centered in the origin. Okay? Then this function constructed with this k-vector valued monogenic function, of course, vanishes in the boundary. On the other hand, after some direct computation, we obtain that C psi fk equals 0. I mean, the sandwich operator of this function u is nothing more than C in fk. But remember that that m is to k. And following the above formula, sorry, we little bit just to show you, okay, here, fk, and here m minus 2k is 0. And for that reason, because m equals 2k, we obtain that, in fact, it is 0. This means that this function u is indeed inframonogenic function, which is, of course, not identically 0, which vanishes on the boundary of the domain. Of course, this means that in Abin dimension, the Dirichlet problem is ill-posed, as at least it has not a unique solution. Okay. What about existence? It is possible to prove that exists the solution of a Dirichlet problem for a ball in the even-dimensional case? No, the answer is not. It's not, and at least in general, okay? And the following counterexample is a very simple counterexample. I will not explain here why we ensure that this problem has no solution. Just I present the problem. Okay? We assume R4. You take the case of R4. It's a very simple case when, of course, 4 is an even number. And we consider this problem where the boundary data is simply a polynomial, a two-vector valued polynomial. Okay, in this case, it is proved that this problem has no solution. For that reason, we can say that the even-dimensional space E is somewhat pathological because the Dirichlet problem has no solution in general, and it's not valid the uniqueness of the solution of the Dirichlet problem. Okay, all the results presented here in this, I think, brief. I don't know what time I took, but were reported in this paper, recently published paper, published in a Journal of Differential Equation, and there you can find all this the proofs of the result I presented here. Here there are the reference, the book of Stein, Singular Integrals and Differential Properties of Functions, and the paper, a very seminal paper of Whitney, Analytic Extension of Differentiable Function Defined in Closed Sets. Okay, that's all. Thank you very much for your attention.
Okay, thank you very much, Professor Abreu, for this engaging talk. Now we are open for questions from the audience. Does anyone have any question? Yes. I'm not sure if this is a question. Okay.
Thank you.
Yeah, I maybe have one question. You actually addressed this during your talk, but I think it's interesting anyways to comment a bit more about it. It concerns the regularity of the function g. So,
Yes.
I mean, from this Poisson formula, of course, it makes a lot of sense to choose C1. But then, of course, since you have this Dirichlet condition, then one would expect that there is perhaps something in between. But then at the end of your talk, you clarified that your feeling is that this is false. Can you tell us a bit more? Why do you think this might be perhaps impossible?
Just a moment. Let me present again because I.
Oh yes. Yes.
Just a moment. Okay. You mean the regularity of the function g?
G1, exactly.
G in this.
It
in
is
this problem.
somewhere-
Okay.
Yes.
Okay. Okay. Up to now, we need, in fact, that this function g belongs to a special space of functions, which is precisely these Lipschitz functions, because we don't know, for example, what happened. Just a moment here. We don't know if this Poisson integral, if the Poisson operator acts from the space of C1 function to C1 function. We didn't know.
Okay, so this is the main obstruction.
Okay, we need that. Not just this. This is one of them, but
Okay.
Also we have this one. Here we need some kind of exponent here, smaller than 0, smaller than 1. Here we need an exponent smaller than 1 to use it to obtain some estimations, and for that reason we need that in combination with that is that we obtain the result. It's necessary to obtain some kind of, of cancellation. Okay, we need this, that the function f belongs to this space. It's a matter of the method. Maybe it is possible to produce another method, to use another method to prove a result for a function in just C1. But taking into account our experience in studying singular operators, singular integral operators, for example, which is a very classical result due to Privalov and Plemelly, is that the singular operator behaves invariant in the Holder classes. So the Holder classes behaves invariant under the action of the singular operator with alpha between 0 and 1. But for example, if we just assume a C1, a C function, a continuous function, then it is not true. The singular integral operator does not act between continuous function appropriately, but it acts appropriately in the case of Holder functions. For that reason, we think, but we have not any example, that it will be possible to construct an example of C1 function, just a moment, of C1 function G defined in the sphere, such that the Dirichlet problem has no solution for inframonogenic function. It is just a conjecture, but we don't know. Okay.
Okay, thank you very much. I think Duan has another question. If Duan, can you hear us? Yes.
Yes, yes. Exactly. Just continuing the discussion that you have with respect to the question of Santiago in the slide 21. 21.
Slide 21.
Slide 21, I think it was. Yes.
Let me go again to that slide because I don't know. Just a moment. I will share again because I lost the. Okay. Slide. Yeah, here.
21, yes. Here where you have these two estimates, right?
Mhm.
Your parameter alpha is between 0 and 1, right?
Yes.
So my question is, if alpha is larger than 1, then it doesn't make sense, right, for harmonic functions to have this estimate, right?
Mhm.
Because probably probably they are bounded and it's not
Yeah.
interested in your case,
Yeah.
right? Okay.
Yeah,
So
yeah.
this just was my
Okay. Thank you. Thank you.
yes. Thank you very much. This and maybe another philosophical question, right? Because you were talking about singular operators, singular integral operators, right?
Yes.
But if in this context you have something like oscillating singular integrals, right? This kind of generalization of singular integrals that, for instance, Pfefferman introduced like in the 70s.
Uh-huh.
But it's just philosophical question. I don't know if
Yes.
maybe your setting is not.
No, really, I don't know. I don't know. I don't know. I don't.
Okay.
Nothing. Thank you very much.
The paper, maybe.
Yeah.
The paper,
Yeah.
then.
Okay. Thank you very much.
Thank you very much.
Okay, so thank you very much once again for our speaker. And then we continue in 10 minutes or so.
Okay.
Thanks.
Thank you to all of you.
Okay, so thank you very much. It's my great pleasure to present our last speaker today, Professor Juan Boris Reyes from the Instituto Politécnico Nacional in Mexico, who will talk about the homogeneous Riemann boundary value problem on rectifiable open curves. So, Professor Juan Boris Reyes, thank you very much for accepting our invitation, and please continue with your presentation. Thank you.
Thank you, Professor Duban. It's a real pleasure to me to talk about this subject, classical subject of complex analysis in one complex variables. First of all, I need to thank all organizers of this very interesting conference, because from Latin America, as the first days was remarked, it's not always easy to have contact with the rest of the world in mathematics community for very different reasons. So I evaluate this initiative as a very, very nice and very good for many of countries in Latin America to have this possibility to share results, or in some cases experiencing one topics, develop it in universities and research centers located in Latin America. When I received the invitation to take part of this conference, I was thinking what would be interesting to present in order to follow the main idea I understand of this conference. That is, when I received the invitation, I feel that the intention was to observe in some different approach what mathematics is developed here in Latin America. Of course, during the first and the second days, we are looking for that many interesting topics are developed for the author and the speaker already take part in the conference. And I decided to talk small talk about the very old problem of the theory of complex analysis, which is very well known, but unfortunately there is not so developed nowadays. Riemann boundary value problem on open curve in the complex plane, in particular in rectifiable open curve, is a problem which is not so much developed nowadays. I will try to present in this short talk an approach to give an idea and a motivation about how it's possible to solve or to present the most general situation about the solvability of the homogeneous Riemann boundary value problem on rectifiable open curve. I will try to give the most essential idea about this problem. In the classical setting of the homogeneous Riemann boundary value problem on boundary dated, it's assuming to be smooth Jordan open curve with extremum E1, E2 of the complex plane C and prescribed Holder continuum coefficient G, which is a function, fixed function, fixed in the curve gamma with value in the complex plane, such that the function do not null in any point of the curve. And the idea is to try to see if possible to construct an analytic function in the complex plane less the curve. Also, it is interesting to see if the solution has finite order at the infinite. That is, continuous extension up to the curve less the extremum of the curve. From the left and from the right, where it is possible to talk about the left and right, for that reason it's necessary in open curve to put out the end of the curve in accordance with the sum conjugation boundary relation. I think that everybody remember this, but I will come back to the condition later on. The main goal of this small talk is to present a brief review of result on the homogeneous Riemann boundary value problem for analytic function with a very general boundary date. The Riemann boundary value problem for analytic function on one complex variable was extremely studied by this famous mathematician Gahoff, Michel-Willis, and Yankee Lu. I am presented the very well-known monographs about this study by the author I mentioned. And now I will try to, in symbol, to formulate the homogeneous Riemann boundary value problem. The problem is to find if it exists an analytic function phi definite on C less gamma, where gamma is, as I talked before, a rectifiable open curve in the complex plane, up to gamma, which, remember, is gamma plus the endpoint. Also, we are looking for solution with finite order at infinite. It is in symbol that exists R greater than 0, a positive R, and N and 0 number, such that out of the ball with radio R, we have the development in series of the solution, which satisfies the inequality 1. Observe that we are given with this estimation for the solution, in some sense, an integrable condition for the solution near to the end of the curve. For each n. Moreover, the boundary value of the solution P along the left and the right angles of gamma wish will be denoted by phi plus minus respectively, and satisfy the condition, the traditional condition of the factorization of the fixed coefficient G. That is the formula 2. We will introduce the denotation Bn gamma, the set of analytic function in gamma wish, that is C less gamma, continue up to the gamma wish, from the left and the right, with order n, that is the maximum of the coefficient in the series of the solution, which is coefficient is not null. That is using this series representation for the solution, we are looking for in symbol of the maximum of the coefficient not null in this series. Obviously, for n greater than, that is a positive n, a function in this class Bn has a pole of order n at infinite. For n negative, has a 0 of order minus n at infinite, and for n equal to 0, take a finite value at infinite. That is something regularity at the infinite. The class of regular function at infinite, that is less or equal to 0, will be denoted by B0 in gamma. The homogeneous Riemann boundary value problem permit to consider, because it's an homogeneous problem, to study the number of linear independent solutions, which I will denote it by Ln. When gamma is smooth and G satisfied in gamma the Holder condition, as is classically considered, and this, of course, this function do not vanish anywhere on gamma, then the number Ln is exactly equal to k minus n plus 1, where k is minus lambda 1 minus lambda 2 for lambda 1 and lambda 2 interiors, such that satisfy the next condition. That is alpha 1 plus lambda 1 even alpha 2 plus lambda 2 have to be in the interval minus 1, 0, where alpha 1, alpha 2 are given in terms of the value of the continuous logarithm of the coefficient gamma G, in both end of the gamma. For that reason, not so many years ago, the people start to understand that the solvability of the homogeneous Riemann boundary value problem in the continuous statement for open curve will depend about the geometric behavior of the end of the curve. The equality Ln equal to 0 means that the homogeneous problem 2 has no trivial solution. If the smoothness condition for the curve is violet, then already for rectifiable curve, the pictures of solvability of the problem 2 can be changed, and even you can obtain an example of the homogeneous problem where the number of linear independent solutions could be infinite. That is, there exist some works where example could be presented where you can see that the dependent of the geometry behavior of the curve at the end is very determined to calculate the number of linear independent solutions of the problem. Classes of complex plane open curve for which the number Ln depend on the character of the behavior of the curve in the neighborhood of its ends have been dealt with many authors. I am listing here in this slide and the next what I consider the most representative author who pay attention about this very, very deep problem on the classical Riemann boundary value problem on complex plane. Professors Saifullah, Selim, again Saifullah, Danilov, Katz, Kutulu, Peña Pere, and myself, Plaxka, and Kudavila are, from my point of view, the author who pay attention very deeply about this situation. What I will present it to you is my approach of how it's possible to give a very general data of the statement of the Riemann boundary value problem where you can conserve the standard statement of the problem. For that reason, I will give some denotation and definition. I suppose that because it's a very standard complex analysis, what I am talking about will be very clear for all who are decided to take a part of this talk, which now I take the opportunity to thank for decide to use this time to hear this very simple and small talk. I call the pair gamma G compatible if the Cauchy type integral of the logarithm function of the function G is analytic in the complex plane, less gamma continue up to gamma which from the left and from the side. All conditions considered in almost all paper about the solvability of the homogeneous Riemann boundary value problem assume conditions such that conditions from gamma and from the coefficient G assume conditions such that what I am talking about compatibility of the pair is satisfied. As I mentioned before, Lngx represents an arbitrary continuous branch of the logarithm function, and the second condition for the compatible pair is that exists two numbers qk, k1, 2, corresponding to the end of the curve, such that for any set in the neighborhood of the extreme, satisfies the condition 5. Observe that I am considering in the estimation number 5 the exponent of the real part of our Cauchy type integral number 4. Again, we are looking for what are the most general conditions from the curve gamma for the geometric behavior of the curve gamma and the fixed function G, such that I can expect it to be solvability the homogeneous Riemann boundary value problem in the standard possibility as is given by the first standard and classic book I mentioned at the beginning of this small talk. The second definition is coming about the characteristic lambda k of the pair, compatible pair, at the end of the point. These characteristic number are defined as the infimum of the k such that the last 5 formulas holds. That is, in the formulation of the compatible pair, we are talking only about the existence of such number qk. But for the concept of characteristic, I am talking about the infimum of such q satisfies formula 5. The last and the most important definition is the concept of the index of the problem 2 with this general intention I am trying to explain. The value of the index of the problem 2 will be definite dependent of the situation of the pair gamma g. If gamma g is compatible in the sense before I mentioned, and the absolute value of the characteristic lambda k are finite, then the value of the index by definition will be minus lambda 1 minus lambda 2. This is the middle equality in this definition. The other are the extreme case. For example, if the pair gamma g is compatible, but at least one characteristic number lambda k are minus infinite, then the index will be definite by infinite. The rest case is when the pair gamma g is not compatible in our definition. In that case, the index will be definite minus infinite. This notion of index of the homogeneous Riemann boundary value problem is a very general approach of a definition of index of the problem, which will help to calculate the number Ln, that is the number of linear independent solutions of the problem. In the standard case, when you are working in a smooth curve and function g, or Holder function g, then it is very well known that the index defined by the variation of the argument of the value of function g in the extreme of the curve represent the linear independent dimension of the solution of the solution class, of the homogeneous Riemann boundary value problem. And what we try to concern with our notion of index is a way to conserve this situation. But when you are not assuming any condition about the curve gamma, of course, we are working with a continuous statement of the problem. For that reason, gamma is considered a rectifiable curve, open curve, and function g is assuming to be Holder continuum. Probably the last definition is that to say that a pair gamma g is said to be skew compatible if the Cauchy type integral 4 I presented before is only an analytic function in the complex plane less gamma continue up to gamma wish from the left and from the right. That is, skew compatible is the only first condition of our definition of compatible. And now the first proposition is the following. Under our assumptions, every solution phi in class Vn of gamma of problem 2 admit always the representation given by formula 6, where C is an analytic function over the complex plane less that end of the curve. The order of the solution are n at infinite. That is, with this general data of our problem, we can conserve the idea of giving the expression of the solution when it exists of the homogeneous Riemann boundary value problem in terms of an analytic function out of the extreme point A1, A2. For member of the audience is to know about the Riemann boundary value problem, know that this general function C is exactly what in the standard case was called the canonical solution of the problem. Let me say what we will understand about the picture of solvability. The picture of solvability of the problem 2 will be referred to be classic when the following condition hold. First, there exists an integer n such that problem 2 has not trivial solution in the class Vn gamma. And the second, the number of linear independently solution of the problem 2 in Vn gamma is finite for any integer n. That is what all authors already mentioned before, try to prove under their condition, particular condition they are assuming. The next proposition say that if you have a pair compatible, then the general solution of the problem 2 in Vn is given by the expression 6 if and only if the function C be meromorphic in C less the end of the curve, possessing singularity in AK for both of finite order greater than this characteristic value I mentioned before. Now, I will introduce what is called canonical function from the problem 2 with finite index according to the definition 3. That is the function we can construct using the characteristic value lambda 1, lambda 2, and using also the Cauchy type integral gamma. Of course, for any set belonging to the complex plane less gamma. The canonical function with this very general assumption can be proven that has the following property. This function is not null for any set. It is not vanished limited, that is, this function can be approached from both sides to gamma wish and near to AK for k equal to 1 and to 2. This canonical function X set satisfies the inequality 1, that is the estimation from the problem, from the statement of the problem. And the last is that this canonical function has finite order at infinite equal to minus kappa, which is the index of our statement of the Riemann problem. The first theorem gives to us almost a characterization of the solution of the homogeneous Riemann boundary value problem. Let the index of the problem 2 be finite. Then the general solution of the problem 2 is given by this expression A, that is, using the canonical function and a polynomial, which is the solvability subject or dependent with the condition if and only if there exists two numbers tau k, real numbers tau k, k equal to 1, 2, such that the estimation number 1 satisfied, where in the neighborhood of each endpoint ak equal k equal to 1 and 2. One corollary is that the canonical functions represent the non-trivial solution of the problem with the lower order at infinite. A second corollary, if we suppose that the index of the problem 2 is finite and the pair G with the inverse of the coefficient also compatible, because to be a finite index, remember from our definition, the pair gamma G has to be compatible, but now we are assuming that also gamma and the inverse of G be compatible, then the general solution of the problem is given by the formula before A. One of the results, I think, starting to be more interesting, is that if we suppose that the index of the problem 2 is finite and its general solution is given by formula A, then what's happening in dependence of the value of the index kappa. If kappa is less or equal to 0, then the problem 2 does not possess solution vanished at infinite. Otherwise, if kappa is greater than 0, then problem 2 has k linear independent solution that vanish at infinite. That is, we are conserving the classical statement of the Riemann boundary value problem with this general consideration. One result more is that if you have the pair gamma G compatible, then the following assertions are true. First, if at least one characteristic number lambda k is equal to minus infinite, then for all n integer, the problem 2 has infinite number of linear independent solutions in Bn gamma. Remember that in our definition of index of the problem, under assumption of compatibility of gamma G, you have those two possibilities. One, both characteristic numbers are finite, or one of them are absolute value infinite. That is, lambda k for one of two, k1 or k2, could be minus infinite. In that case, we also can prove that the number of linear independent solutions in the class Bn gamma is infinite. In the other case, if the index kappa of the problem 2 is finite, which is the other possibility under the assumption gamma G compatible, then the number of linear independent solution in the class Vn gamma is given by the formula kappa maximum of the numbers kappa plus n plus 1 0. That is, in the case of kappa plus n plus 1 positive, then that is the exactly number of linear independent solution in the class Vn gamma. This proposition are real, very special condition, which is coming from the work of Professor David Katz, who died 3-4 years ago. He was a very well-known expert in the study of Riemann boundary value problem and was the first to consider this condition 10 as a particular case of possibility for the compatible pair for study the Riemann boundary value problem. Let us assume that gamma is a rectifiable Jordan open curve, G as before, not null function in any point of gamma, Holder continuum in gamma, and we are assuming that the order of the Holder space, which is belonging to the function G, satisfy the condition nu greater than 1/2 or even nu equal to 1. But it's necessary to assume this condition 10. Again, in a neighborhood of each endpoint ak, k equal to 1, and then the problem 2 has a classical picture of solvability. This is a result, a proposition, which is proved directly following the previous result I presented to you, which is remembering the work and the approach of Professor Katz. The second proposition, which is also an interesting and very general condition, is you suppose gamma a Jordan open curve, a regular open Jordan curve. That is what means regular. It is that the quotient of the length of gamma inside any circle of the radius of the circle is less than some fixed constants. That is, you are consider the condition or the geometry condition of the curve such that the length of the part of the curve inside any ball with center in a point T of the gamma is exactly proportional to the radius of the ball. If you introduce the denotation G and T equal to exponent of an auxiliary function ft for all t in gamma, such that this integral converges uniformly in gamma, then again problem 2 has a classical picture of solvability. This is a second explicitly condition which is possible to obtain classical picture of solvability of the homogeneous Riemann boundary value problem following our result I presented before. Now I would like to talk about the Picard-Privalo alternative for the solution of the homogeneous Riemann boundary value problem. These Picard-Privalo alternatives are in the direction of to consider simultaneously both homogeneous Riemann boundary value problem, the standard Riemann boundary value problem with coefficient G, and the second one, the homogeneous Riemann boundary value problem, but with the coefficient, the inverse of the function G, that is equality 12. This problem, again, will be of interesting and can apply all the result I mentioned before, but I have to change a little bit for the notation, and for convenience, I will change a little bit some of the denotation. For this problem in the formula number 12, the number of its linear independent solution will be denoted now Lm over star. Again, Bm gamma is the same class of analytic function with order m at the infinite, and again the number of this solvability will be trough kappa over star. In a similar way, the order of the problem 12 will be definite, and again we will use this variation of the symbol. Now will be kappa over star. The following theorem give how it's presented the Picard-Privalo alternative when you try to study simultaneously both homogeneous problems. Let gamma be a rectifiable Jordan open curve, and suppose, as before, that coefficient gt are not null in any point t of gamma. Then the following Picard-Privalo alternative are valid. That is, you can assert that if Ln greater than 0, that is, the number of linear independent solutions of the homogeneous problem with coefficient g are positive, then you can prove that the number of linear independent solutions, it is Lm star, are always less or equal to the maximum of the numbers 1 plus n plus m or 0. The second alternative is that if one of the problem 2 or 12 has solvability order at finite, then this relation between these two values are true. In the case of the space, the class, V1, at least one of the problem 2 or 12 does not have not trivial solution. And the last one is if one of the problem 2 or 12 has finite number of linear independent solution in any class Vn gamma, then the other does not have not trivial solution in any Vm class. The alternative Picard-Privalo can be presented also under skew compatibility condition of the pair gamma G. That is, you can prove that there exists a class Vn where both problem 2 and 12 have not trivial solution. It is number Ln and Ln star are both positive, and according to the previous theorem, one concludes that both are finite. And the second is that there exists a class Vn where both problem 2 and 12 have finite number of linear independent solutions. That is, both Ln and Ln star are finite, so are for any n, because the positivity type of of this succession of all values of the number Ln. That is the value of this limit of this succession. One theorem more. Let the pair L gamma G skew compatible, then for the validity of the alternative PP1 is necessary and sufficient that the number nu bar on AK are finite for both k equal to 1 equal to 2, and the same for the validity of the alternative PP2. It is necessary and sufficient that nu underbar in both AK are also finite. Suppose for this corollary again that the pair is skew compatible, then the problem 2 has a finite number of non-trivial linearly independent solutions in a class Vn. It is necessary and sufficient that the number nu over bar on AK for k equal to 1 are finite. And the last corollary in this sense is the expression you can obtain for the value of the index of the Riemann problem number 2 when you are assuming that the pair gamma G are skew compatible, and also the number nu under bar are finite. The index is given by this expression. The last corollary is that if the pair gamma G is Q compatible and the nu over bar are finite, then the value of K and kappa coincide. I am coming to the last part of this small talk, and I would like to give an approach of the solvability solution of the homogeneous Riemann boundary value problem in the case of the index are infinite. For that, I give the one definition more connected with the pair skew compatible. Suppose gamma G is B is Q compatible, then the order of this pair is by definition this number I am given in this formula. Rho gamma de G are equal to infimum of all nu positive, such that this limit exists. Given there, we are considered a skew compatible pair. In the case of the index kappa be minus infinite, then you have this situation for any solution in class Bn gamma. Solution of the problem 2 is necessary for the number I introduced before, less 1 over 2, sufficient that this expression you have, or you have the representation of the solution in the formula number 11, where the function phi are an integer function of order exactly in the number I introduced before, so that you have the relation between these two numbers, where you are assuming this asymptotic inequality for the function phi. Here, this new number rho on phi are the limit of this expression, where m phi are the maximum of the function over the ball of radio r, and it is identified with the integer number or order of integer of the function 5. These two small papers were published in 2021, where I tried to resume all the ideas I presented to you today. Thank you very much.
Okay, Professor Juan-Borí, thank you very much for your very interesting talk. And I also noted that you were very precise with the time, which is a good news, essentially for the last talk of the day. So let me see. We are open for questions now. If someone wants to ask something to Professor Juan-Borí Reyes about the presentation, please go ahead. Okay. Okay, maybe I myself can start with some question, right? Okay.
Sorry. Will we welcome your question, Professor Duban?
Okay, thank you. No, just it's more. I don't want to make technical questions, right? I prefer maybe for this part of the presentation to make a philosophical question, right? You start constructing this analytic function, right? That is analytic in the complement of one curve, right? And continuous in the closure, right? And continuous in the closure. My question is if this problem, or if you know literature about this problem in several variables, where you consider, let's say, instead of a curve, one consider, let's say, the complex surface or something like that. If you know about extension of this problem in higher dimensions, this is my question.
Well, you are trying to put me in the way I do not like it to talk, but I will because exactly this all standard problem about Riemann boundary value problem is already extended for high dimension using the analysis, which is very well known as Clifford analysis.
Okay.
That is using Clifford analysis as one of the more, or not say the most important generalization of the one complex analysis. You can see several papers where all these ideas are extended, are very important mathematicians in different countries who are try to develop this very important classical problem of analytic functions theory for high dimension using Clifford analysis. You can see, for example, or I can see that one of the mathematicians who approach this problem for high dimension will take a part in this conference. She will talk on Friday, the first talk. But already we hear the previous conference, the previous talk by Professor Ricardo Abreu, who also worked in this approach. I would like to mention, because it's an honor for me to mention, Professor Klaus Gullebeck and Wolfgang Sprossig from Germany, and some others who try to develop this very interesting situation in high dimension. I have to be included in this group as one of the author, the mathematician, who, following the suggestions received by Professor Michael Shapiro from Instituto Politécnico Nacional, and also from Professor Richard Delange and Franz Sommen from Ghent University, who at the 90s, at the beginning of the 19th of the last century, in the time was the first contact with all these famous mathematicians. They give to us the motivation to study this generalization.
Okay.
It's a pleasure, and I thank it to you to ask about this possibility, because as I mentioned at the beginning, I would not like it to talk about this current development of the problem. I would like it to keep in the standard problem for complex analysis. But thank you very much anyway.
Oh, thank you. Just it's very interesting, of course, and you give me a better perspective. Just as a curiosity, I can share with you and with Professor Abreu that I met Professor Frank Sommen when he still was in Ghent University. I graduated from Ghent University, and now as postdoc, I am located in his former office. Then it's a big responsibility to do mathematics in his office.
It will be very difficult for you,
right, to
conserve what all very famous results and Clifford analysis out of such a office. For Ricardo and myself, it was a very pleasure to visit Ghent for several times and to collaborate with this very important mathematician of this area. Really, we have several papers together with him, with Fred Bragg, Henny de Schepper, Richard Delange, etc. Thank you very much to remember me in such a very important step of my life which is ended very near.
Thank you very much for your
mathematician, I say.
Right. I am sure about that. Yes, you will continue enjoy. Not just then. Thank you very much. Maybe let's finish the program at this moment. First of all, I want to thanks to all the attendees who were present during the last sessions today. We are going to continue our scientific program tomorrow. Tomorrow we start. According to our scientific program, we are going to start at 3 p.m. in Central European Time with the talk of Rafael Alvarez, just to let know to the audience that tomorrow we are going to have the in-person program in the National University of Colombia, and this program will be shared by YouTube and by Google Meet also to the attendees. So we will be here online, right? But then there will be an in-person program in the National University of Colombia. So thank you very much. And thank you, Professor Juan Boris Reyes, for this very nice talk. And then see you tomorrow in our conference. Thank you very much.
Thank you to you. Bye.
Bye.
See you tomorrow.
See you tomorrow. Alexandra, listo. Finalizamos la presentación del día de hoy.